Morning, everybody. Okay, so what we're going to be doing in today's class, we're going to finish the PowerPoint presentation. We did not get to finish it in the last class, and then we're going to start a review of systems, and eventually we're going to start the Laplace transform review. Any questions from previous lecture? Zoom?
Yeah.
Why?
There's a couple other instructors that we can log in from home to do lectures and stuff like that on Zoom. I was just wondering if you would include that.
There is not going to be a Zoom. The lectures will be recorded. You can watch them afterwards.
Okay.
The problem with the Zoom is that because we have the video conferencing, I mean, if there is also a Zoom, it's become distracting. I'm not going to be able to look at you, look at the class, and also pay attention to the Zoom. Does that make sense? I mean, we can take off one of the three, but we cannot have the three of them. Make sense? Like if somebody is on the Zoom and typing a question, I'm not going to see it. And then they're going to be frustrated. You're not paying attention to me. And I asked a question. You understand that? Go ahead.
I think what he was asking is if you could like stream your screen on Zoom. Because I don't know if they can like.
I understand. If they is that what you're asking for? You're asking for to access it from home.
Yeah.
If somebody is asking from home and he did not, I asked, is there any question? And he types a question, I'm not going to see it. Does that make sense?
Yeah, but I think he wants to like.
No.
solely see the PowerPoint.
No. They see the PowerPoint there.
Oh,
That's what they see there.
I don't know.
No, they see the PowerPoint. The Zoom is like so you can access it from home. Hopefully, everybody is going to be able to attend the class. I mean, nevertheless, in the circumstance where you're not able to attend, you can always watch the lecture and ask if you have any questions. Make sense? I mean, we tried the Zoom and it really did not work because, again, there is 3 audiences and nobody is going to be happy. If I pay attention to what people are typing, people in the class like feel left out. If you do not pay attention to the people on the Zoom, they're going to feel left out. So since we have the video conferences, I think this is the best setup from my experience. I mean, potentially we can try it, but again, I doubt it's going to work as efficiently. Okay, so in the previous class, we talked about the topics that we're going to be covering in this class. Anybody still remember any of them? Systems, review of systems. No, the topics that we're going to be covering this semester, sorry. You're going to be our root locus guru. Root locus. Let's start them in chronological order. What is it we're going to be doing first? Laplace. After we do Laplace, what are we going to use Laplace for? We're going to use Laplace to model systems. Makes sense? So we're going to take a system, model it with Laplace. After we model it with Laplace, what are we going to do? Block diagram reduction. We're going to try to reduce the blocks so it's just a single input, single output. After we do that, what are we going to do? Yes, we're going to look, we have a block diagram that represents the system. We're going to look at the response of the system, the first order, second order, higher order systems. And then we're going to start looking at the system. We're going to look at the stability of the system. What else after stability? We're going to look at the steady state error of the system. And then we're going to start designing a controller. In order to design the controller, we're going to need to learn the root locus. We're going to learn root locus, and then we're going to start designing different controllers. Make sense? And then after we finish that, we're going to look at modern control systems. And then finally, we're going to look at the analysis in the frequency domain. Sounds good? Okay. So in the previous class, we looked at the block diagrams that are involved in the design process of a control system. And these block diagrams represent what we're going to be doing in the course, from modeling the system to reducing the system to designing the controller to analyzing and testing. And again, keep in mind the block diagrams here might be misleading because one block is going to involve most of the semester, and 3 blocks might be just a quick review. Make sense? And then we looked at an example of an antenna, a dish antenna, that we want to try to control the position for. And we said one way to control this azimuth position of this dish antenna is to use a potentiometer. Make sense? Potentiometer, you turn the knob right and left, and therefore the antenna will respond to that. Okay, so we're going to use the requirements, the design specifications, and then the desired transient response and steady state errors. All these are going to come into the design of the controller that is going to control this dish antenna. So what we're going to do is we're going to create a schematic that represents the system. So this is the layout of the system, the antenna and the potentiometer, some more details in order to measure the position of the antenna. What is it we're going to do? How would you measure the position of the antenna? If the antenna is moving right and left or rotating?
Have an origin and measure it from the origin.
Yes, but like what device would you use? Some gears that will translate into a potentiometer. Does that make sense? So I can take the shaft that is rotating, connect it to some gearing system, and the gear, there's a translation from a gear to a gear, but eventually all the gears are connected to a potentiometer. When the antenna rotates, the potentiometer is going to rotate in response. And what is that rotation going to give me? A change in the resistance of that potentiometer, which I can translate it into a voltage. Does that make sense? And similarly, in order to set the position of the antenna, I have a potentiometer that is going to generate a different voltage, and accordingly, the antenna is going to move. Together? Everybody sees that system? Can picture it? Okay, so this is the schematic of our system. We have a potentiometer that we rotate. It has a voltage, and then there's a voltage reading. There is another potentiometer that is connected to a gear that is connected to the shaft of the antenna dish. And these are subtracted from each other. And therefore, this will give me, what is this reading that is going to be the result of this subtraction? What would you call this signal here? If you have a choice.
Differential.
Excellent. What would you call the signal then? What does this signal represent? If this signal is 0, what does it mean?
There's no difference.
There is no difference. Then if there is a difference, what is that difference? That is the error between where I want the potentiometer to be and where the actual dish is. Make sense? So this error signal is going to drive the motor and make it either rotate clockwise or counterclockwise. What is the ultimate goal? To get to an error that is a 0. Make sense? Okay. Now when we take this error signal might be coming from a very small voltage. I might connect this to a battery, connect this to a battery. And therefore the voltage that this potentiometer or these two potentiometers are giving me are very tiny. What do I have to do in order for them to be able to drive this motor? I have to amplify them. So therefore, I'm going to take this small voltage, I'm going to amplify it, and then I'm going to apply it to my motor. And that voltage is going to cause the motor to rotate, and according to the rotation of the motor, we're hoping that this error is going to get smaller, eventually it's going to go to 0. Okay. Now we see also here the inertia and the viscous damper. What does these represent? Anybody knows? I mean, we're going to see them later, but anybody knows what the inertia is, what the viscous damper is? I mean, this dish is a load on this motor, isn't it? I mean, if I have this motor rotating alone, it's going to be different than if I install all this dish on top of it. So to represent this load that is on the motor, I represent it with the inertia and the viscous damper. Make sense? And we'll see them again when we look at the mechanical systems. Okay. The next step is we're going to draw a functional block diagram. So we're going to take the schematics that we created, and we're going to plot our functional block diagram. Our functional block diagram is going to look something like this. We're going to have the angular input that we're trying to set the antenna at, potentiometer, a voltage, and then a voltage that is coming from the current position of the antenna. And the difference between them are going to give me my error signal or my actuating signal. And this signal is going to be amplified and then applied to our motor. Make sense, everybody? Okay. Okay, what is the next step? We're going to try to model all these components that we have in our system. Now, some of these small components are going to be straightforward. A potentiometer might be just a constant multiplied by whatever input. However, some other components might require us to know how that component operates and what we're going to be using in order to model these systems. We're going to be using the laws that we know from electrical and mechanical systems. Kirchhoff voltage laws, Kirchhoff current laws, Newton's laws, any laws that applies to that physical system. What are these modeling going to give me? A differential equation. I'm going to get a differential equation that represents how that component is operating. Make sense? What happens if I take the Laplace transform of that differential equation? I can get...
Is it algebra? Or is it?
What will it give me? What is it? What else? What if I take the Laplace, and this is my output, this is my input, and then I write the output over the input? Transfer function, yes. It will give me a transfer function. So I can go back to my system here and represent each one of these blocks with a transfer function. Make sense? And then I have all these blocks. What can I do based on what we said we're going to do in this semester? Simplify it. Take all these blocks and just reduce them to a single block. Okay. So we can reduce all these blocks using the modeling that we've done and the block diagram reduction. And then we have a system that has an input and it has an output. Any questions? Okay. Now some of the inputs that we will use to analyze and design the systems that I'm sure you guys are familiar with. First one is an impulse function. What is the impulse function? Yes, but what else we know about this impulse function that nobody else knows? How is this impulse? What is, like when we write an impulse like this and we put around it like a 1, what does this one represent?
The area under.
Excellent. Excellent. The area under the function. The impulse function is defined by an area. The area underneath this function is 1. Together? What is the magnitude?
1.
No. The area is 1.
Okay.
What is the magnitude? It goes to infinity. What is the width of it? Goes to 0.
Yeah.
Make sense? So please remember this. Anybody's gonna remember this? I'll ask you at the end of the class. Okay, so if this is my impulse function, always think of impulse function as the following. This is a delta, and this is 1 over a delta. And what does delta go to? 0. So if you look at this rectangle, what is the area of this rectangle? 1. 1 over delta multiplied by a delta. The area is always 1. However, what's going to happen if I make delta go to 0? The width is going to be 0. What is the magnitude going to go to? Infinity. Is that clear? Make sense? Now, the exact shape is not important. It could happen like this. It could happen a triangle. What matters is the area is always a 1. This 1 that we wrote, when we write the impulse like this, represent the area of this function. Okay. What does this, why is this, what do we use this delta function for? Impulse response. Excellent. Excellent. If I have a system in a box and I tell you, oh, I have this system that I do not know what it does, and I want you to find out what this black box is, what do?
Shoot an impulse through it.
Yes, apply an impulse to it. What is the output of this black box is going to be? The impulse response. Is that clear? Does that make sense? Everybody remember something like that? If I apply an impulse, I'm going to get the impulse response of that system. And why else is this impulse function important? Let me try to channel my energy to you and see if you can. What is the spectrum of this impulse look like in the frequency domain? Like if I take,
Like a sink.
okay, at least a good guess.
Yep.
Any other thought?
Is it constant?
It's a constant. So this is the time domain. In the frequency domain, it looks like this. Make sense? This impulse that we have here in the frequency domain has the frequencies from negative infinity to infinity. Why is that very nice and important? Yes, because this will give me the frequency response also of this system. When I apply this to the system, when I am applying an impulse, what does it mean? I'm trying to apply all the possible frequencies to that system and see how it reacts. Does that make sense? Okay. Another function that we will be using is the step function. The step function is a 0 for t less than 0, and then is going to equal to a 1 or a constant when t is greater than 0. Another function is the ramp, which is t for t greater than 0 and 0 when t is less than 0. Another function is the parabola, which is 1/2 t squared multiplied by u of t. And finally, the sinusoidal signal, sine w multiplied by t. What is w equal to? The font is small, isn't it? What is this w equal to? It is, what is it? Frequency. And what is it equal to? What is the unit of this W?
Radians per second.
Excellent. Radians per second. The second will cancel, and this becomes a phase, radians. And what is W equal to? 2 pi multiplied by the frequency. What is the unit of the frequency? What is it? Hertz. Very good. How is this frequency related to the period of this sinusoidal signal? The frequency is equal to 1 over t. Together? Any questions? Okay. So this is the end of our PowerPoint presentation. And now we're gonna go to our writing notes. Okay. So let's go back to the review of systems. So one of the properties of the systems that we talked about was linearity. What is a linear system?
It has homogeneity and additivity.
Yes, it satisfies homogeneity and additivity. And therefore, if I apply to it x1 and I get y1, if I apply to it x2 and I get y2, if I were to apply to it ax1 plus bx2, I should get ay1 plus by2. Together? Oh. Now again, we said linear systems are simpler to study and analyze, and we have lots of tools that are available that will help us use them and analyze them and design for them. And when we have a system that is linear, the first thing, if we are trying to design for it, the first thing we will try to do is to linearize it, to see if we can represent it by a linear system. Okay. Another property of systems is whether a system is time varying versus time invariant system. What is a time varying system versus time invariant system? As the name implies,
Just varies with
Varies with time.
the system that varies with time. In time varying system, the parameters of the system change with time. What is an example of time varying system?
Car, maybe?
A car, very good. How is a car time varying system?
As time progresses, all the things involved with it change.
What is like a very obvious thing that changes in the car?
The speed,
What else that makes it a varying system?
Mileage,
What else?
oil level,
More obvious than oil.
clock.
Gas.
oh,
I mean, you can drive your car with the car full of gas. You're driving, then the gas is getting less and less. The car is changing, isn't it? Or you could be, giving somebody a ride. You have 4 people sitting in the car. Then they get off the car, and then the car has changed. Make sense? Okay. What is a time invariant system? A shift in the input results in identical output shifted a shift in the input results in identical output, only shifted by the same time shift as the input. So what does that mean? If I come to a system, and I apply an input at 0, and I get an output that looks like this. If I come to the system and I apply the input at 10, what do I get? What should I get if the system is time invariant? The same output, just shifted. Make sense? So if they're the same, then the system is time invariant. Okay, what happens if I came to this system and it gave me the same output, however, this output starts at 9? Is this time varying or time invariant? Time variant. Together? So not only I should get the same output, the shift of the output should be the same as the shift in the input. So if I were to apply this at 10, the output should have shifted to 10. Since it's shifted to 9, then it is time variant. Okay. What is another example of a time variant system that the students will encounter in their capstone? They build their circuit, and then their friend comes and they get perfect results. Then another team member might come and work on it, and then you come the next day, and then all of a sudden the system has changed. Okay. So if we have a differential equations, if the coefficients of the equations are constant, or not function of time, then the system is time invariant.
Dr. Almeida,
Go ahead.
are those dots above your Y prime?
Yes, they are. What are these dots? Anybody familiar with this notation? Second derivative of y by dt squared. You've seen it? Familiar?
I just never seen over the Y. I was just making sure.
That's fine. No, please ask if there's anything not clear. I mean, just ask. But we will see it more. So,
Okay, thanks.
okay, if I have another differential equation where it is y double dot plus 2t y dot plus y equals sine of t. What is this system? Time variant. Why is it time variant? Because we have a function of time that is multiplying the y dot. Okay, another example. If we have a system where y of t is equal to x of 3t. Is this a time varying or time invariant? We'll find out. How do we find out? We're going to take two inputs and see what happens when we shift the input. So this is x of t. What is this x of t minus a 3? What is x of t minus a 3 does to x of t? Right or left? Right, yes. X of t minus 3 is going to shift it to the right. Okay, so if we apply this to our system, which is y of t equal x of 3t, what is the output going to look like for the first input?
Is it bigger times
What else? Can anybody make an informed guess? What happened when I am at -3? Is going to be y is going to equal x of -9. What is x of -9? 0. It's going to continue all the way to -1. When I'm at -1, what is this going to equal to? Y is going to be x of -3. What is x of -3? This point here. So at -1, let me make it to scale. At -1, I'm going to get something like this, from -1 to a 1. Agree? When I am at 0, when t is 0, it's going to be x of 0. This is x of 0. When t is equal to 1, I'm going to be at x of 3, which is this point here. Therefore, it's going to be this point here. This is y of t. Make sense? Okay, what is the second output going to look like? When is it going to start? When t is 0. X of 0 is going to give me this point here. And then when is it going to end? At 2. Is that clear, everybody, how we got it? So just plugging the values of t and see what they correspond to. So when t is 0, this corresponds to x of 0. When t is equal to 1, x of 3. When t is equal to a 2, x of 6, which is this point here. Okay, so is this system time varying or time invariant? Time invariant.
Would be time varying because the shift wasn't the same.
Excellent. I mean, not only the shape has to be the same, these shapes are the same, but this input was shifted by how much? By 3. This is shifted by how much? By 1. Make sense? So here, shift by 3. Resulted in shift by 1. Therefore, time varying. Okay. What are the systems that we're going to be studying in this course? Time varying or time invariant? No. Linear and time invariant systems. Make sense? Linear and time invariant systems. What do we refer to these? LTI. Linear time invariant systems. And hopefully it's clear why is it we are doing linear and time invariant system. Why is it? Because simpler, yes. Okay. Another properties of systems is systems can have memory, or a system can not have memory, without memory. When is it I have a system that has memory? When is it a circuit will have a memory?
Relies on previous results.
Yeah, give me a component that will cause a system to have a memory.
Capacitor?
Capacitor?
Yeah.
Excellent. Excellent. Yes, a capacitor. If you are using a capacitor, if you run the circuit, the capacitor is charged, you leave the circuit, you come back, whatever that charge is still on the capacitor. Make sense? It's going to remember whatever it had before. So circuit or systems with energy storage or storing elements such as capacitors, inductors, have memory. Okay. Another property of systems is whether a system is causal versus non-causal. Anybody remembers what a causal system, non-causal system? Causal. If the output at any time depends on the input at that time, or the time preceding it, then the system is said to be causal. What does it mean when a system is causal? It means the system is non-anticipating. Is that clear? Anybody understood that? So if I have a system, and that system will only give me a response based on the input at this time or the previous time, then the system is causal. If I have a system that will generate its output not only based on the current time, but also the future input, then what is that system? Non-causal. Make sense? How can a system generate an output based on a future input? Is that possible? How? Can a system generate its output based on a future input? How?
Incremental inputs?
What else?
Can it just be a set device?
Okay. Yeah, I'll help. I'll give you hints. So not every system, when it runs, is running live or in real time. Make sense? If it is running in real time, then it's not going to be anticipating. There's no way to know whether you're going to be turning off the light now or not. Make sense? But not all systems are like that. There are systems that are offline or are not running live. What does that mean? I can take, for instance, a file and process the whole file based on, and my system that's processing will know, like if I have a text file that says this is our control class, and I want a system to process this. He can come to see this key. He can still see what's coming after the key. Make sense? Because it's not live. The whole file exists for the system. Is that clear? Make sense, everybody? Same thing, if I have a file, for instance, that has music on it stored, and I want to process it with a system. The whole file, the whole music exists. So even though it's generating the output at this point, it knows what's coming after that, and it can use it as an input. Is that concept clear, everybody? So there is a live system or real-time system, and there's not non-real-time system. If it is a real-time system, there's no way for me to know what the future input is. But not every system has to be a real-time system. I can take a whole file and process it, for instance, to remove a noise from a recording. The filter that's going to process it knows everything that's going to happen in the future. Is that clear, that concept? Okay. So based on that then, is this a causal or not causal system? You tell me. Causal? 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 I need 3 votes before I write the verdict. It is a causal system. I mean, the t plus 1 is to confuse you, but the causality is determined in relationship to the input. Make sense? T plus 1 does not affect the causality. But you can see any output at any time, y at 100, is going to only depend on x at 100. It's not going to depend on x at 200. Okay. X of t plus 1, non-causal. Okay, one more example to confuse you. How about this one? Not to confuse you, or to have your brain work.
Can it be causal?
Causal?
Just the one preceding?
I need 3 votes. Causal or not causal? Causal? How about it is not causal? And since I gave you the answer, tell me why it is not causal.
Negative values, because you say so future.
How? If I take the output at a negative value. Is that what he said?
Yeah.
Yes, excellent. If I calculate the output at negative 2, what is it going to equal to? X at positive 2. So the output 2 seconds ago is going to depend on the input after 2 seconds. What does that make it? Non-causal. Okay. Exactly. Go ahead.
So if, for the last example, the one before the one you just did, if it was y times negative t equals x times negative t, that would be causal?
Yes. That will not be negative t plus 1.
No, sir. Y times negative t.
Y of t equal to Tell me.
I was gonna say, why is it not causal?
The x of t plus 1?
The, equals x or times negative t.
X of t,
The third example you did.
okay. This one?
No, sir, the next.
This one?
Yeah, yes, sir.
Because if t is only positive times, it's fine. If t is 10, this is x of negative 10, it's fine, causal.
Okay.
But what if I generated the output at negative time? What is y at negative 10? Is going to equal x at positive 10.
Okay.
Make sense?
Yeah. Okay.
Y is at negative 10. The input is happening at positive 10. The input is happening after the output.
Okay.
Does that make sense? And that's why it's confusing. Again, y at negative 2. So this is our time scale. The output y at negative 2, this y, is going to depend on the input that is happening at positive 2. So the output is happening before the input. That makes it not causal.
So Dr. Okuda,
Mhm.
if you had the third example, but you said t has to be
Yes,
1
if
or
t is-
greater,
Yes, if t is greater than 0, then it will be causal. Okay. Excellent. Okay, so this is the main properties of the system that we're going to be seeing in the class. Next, we're going to review briefly the coordinate system. Or complex number representation. So what is the first coordinate system that we use to represent complex numbers? We can have them in Cartesian form. If I have a complex number, I can write it as z equal x plus j multiplied by y. What is this j? Square root of negative 1. What else we will see instead of j? I. What else we will see? J with a dot. So all these means this part is imaginary. This is the square root of negative 1. Okay. So hopefully you're just used to my writing. You see how I write it? Yeah, I mean, most likely I'll be writing it like this by default, unless I pay attention. Okay. So this is the real part. This is the imaginary part. As an example, we can have z equal 5 plus j 6. Another form is the polar form. And in the polar form, z is going to equal, we write it as a magnitude and a phase. So e g to phi. Same number can be represented by either. This is magnitude, and this is a phase or angle. Okay, we can write this as r, and using Euler's formula, what is e to j phi going to equal to? Cosine phi plus j sine phi, which is going to equal to r cosine phi plus r plus j r sine phi. So this is in the polar form, this is in the Cartesian form. I can take the polar, I can go from either representation. Familiar? Okay. Another form is the complex exponential form. So I can write it as e to a q, where q is complex, so this is going to equal e to a plus j b, which is going to equal to e to a multiplied by cosine b plus j sine b. As an example, I can have x equals 7 e to j pi over 2. This is going to equal to 7 multiplied by cosine pi over 2 plus j sine pi over 2, which is going to equal to 7 multiplied by 0 plus j1, which is equal to j7. So we might see any of these three forms for representing numbers or variables: Cartesian, the polar, and the complex exponential. Any questions? Okay. Next, we're going to start our review of our Laplace transform. Where have we seen Laplace transform? Differential equations. Where else? Circuits too. Where else?
Signals and systems.
Signals and systems. Where else?
Linear control systems.
Linear control systems. What is the, why did we use Laplace transform in differential equations?
Because they are required by the state to teach it.
It's used to simplify things.
Can you think and tell me? What is the advantage of using the Laplace transform when we solve differential equations?
Turns it from a differential equation into algebra.
Excellent. Excellent. Who answered? Excellent. Because it takes the differential equation and turns it into an algebraic equation. Make sense? Okay. What is the Laplace transform defined as? What is this symbol I just wrote? Laplace. Okay, the Laplace transform of a function is equal to the integration from 0 to infinity f of t e to negative s multiplied by t dt, and this will result in f of s. And this is the definition for the unilateral Laplace transform, and therefore it starts from 0. What is s? It's a complex variable. What is s equal to? Anybody remembers? Okay, I'm going to write you hints, and you tell me. Okay, I know you know the answer, but you don't want to participate. That's fine. I'll write it for you. S is equal to sigma plus j omega. And therefore, when we plot anything in the S domain, even though we might not label the axes, in the S domain, in S space, what is the real axis going to be? Sigma. What is the imaginary axis is? Omega. Omega. Sigma plus j omega. The y-axis is omega, and the real axis is sigma. Okay. There is also the bilateral Laplace transform. How is the Laplace, the bilateral different than the unilateral? Excellent. Negative infinity to infinity, f of t e to negative s t dt, which gives me f of s. Okay. Now in this class, which one of these transforms are going to be using? The unilateral. Now, I don't want anybody to think that in this class we're going to be our focus will be on the calculation of the Laplace transform. We're going to be using the Laplace transform. Make sense? And that's why we're just doing a review of it. But it is very important to understand it and understand its properties to help you understand also the material. So what we're going to do is we're going to be using the unilateral Laplace transform, which is that. Now what we're saying also, we are going to be assuming that all our functions are going to start at 0. If the functions start at 0, what does that mean? Both of these are going to become similar, isn't it? I'm integrating from negative infinity. If f of t is 0 before t equal to a 0, then this and this are going to give me the same thing. Is that clear? Makes sense? Okay. What are the requirements for the existence of Laplace transform? The first requirement, the function has to be piecewise continuous for t greater than or equal to a 0. Remember these things? So for instance, this will have a Laplace transform that exists. This will have a Laplace transform that exists. G of t equal to 0 when t is less than or equal to a 3, and the natural log of t minus a 3 when t is greater than 3. How does this function look like? A 3 before 3 is 0. and this is going to go to negative infinity. Is this piecewise continuous? It's not. And therefore, this is an example of a function that will not have a Laplace transform. Laplace transform will not exist. Okay. What is the other requirement for the Laplace transform? F of t must have an exponential order. And what that means, there exists C and T such that the magnitude of f of t is less than or equal to m e to c multiplied by t, where m and t are greater than 0. What does that mean? If I have a function that looks like this. If I can find a function m e to ct such that at certain point, this is m e to c multiplied by t. At certain point, this function that I'm trying to calculate the Laplace transform is going to be less than m e to ct. From this point onwards, then the Laplace transform will exist for this function. Does that make sense, everybody? So if the function is of exponential order, which means I can come to this function, plot m e to ct, and at certain point t, this point is t, this m e to ct is going to be always larger than this function, then the Laplace transform will exist. If, on the other hand, this function, for instance, looks something like this, this function will not have Laplace transform. Make sense? There's an exponential function, m e to ct, such that the function is going to be always, there's a point beyond which this function is going to be always larger than the function we're trying to find the Laplace transform for. So as an example of functions that will not have a Laplace transform because they are not of exponential order, e to e multiplied by t. LT does not exist. Why? Because this will grow faster than an exponential e to ct. It's going to be beating that function. Similarly, f of t equal t to the power t, Laplace transform does not exist. For the same reason. If I were to plot t, it's going to be always faster than any exponential function. And therefore, the function does not have a Laplace transform. Okay. Now, when we talk about Laplace transform, there is always one thing that we associate with Laplace transform, and that is the region of convergence. What is the region of convergence? Anybody heard of it? The set of values of S for which the integral converges. Which integral? the Laplace transform integral. What is the symbol for region of convergence? ROC, region of convergence. Is that clear? Everybody remember these things? So when we do the integration, we'll do an example in a second, but when I do the integration to calculate the Laplace transform, this will only converge for certain values of S. It's not going to always exist. It will only exist. It will only converge. It will only be finite for certain values of S. These values of S is what we call region of convergence. So as an example, we have x of t equal e to negative at multiplied by u of t. What is this u of t? What is it? Step function? Yes, step function. Why did I have to have this step function here? Because we said in this course, we're going to only consider f of t that is 0 before t equal to a 0. Makes sense? So we're consistent. If you look, it's yes. Here we're saying this function only exists after t equal to a 0. Okay, how do we calculate x of s? The integration. What is the Laplace transform of e to negative at? Anybody remembers? Okay. What is it?
Is it 1 over s?
Close.
1 over s squared.
Farther. What happened to the a? No, simpler.
Is it a over s?
We'll find out.
Just guessing at this point.
Integration from 0 to infinity, e to negative at, e to negative s multiplied by t dt. Agree? This is just plugging the function in the definition. What is this equal to? The integration from 0 to infinity, e to negative a plus s, or s plus a multiplied by t dt. What is this integration equal to? What is the integration of e to negative a multiplied by x? E to negative a multiplied by x over negative a. Therefore, this integration is going to equal to 1 over e to negative s plus a multiplied by t divided by s plus a, and there's a negative sign that's coming from this negative. And what are the limits of this integration? 0 to infinity. And therefore, this is going to equal to 1 over s plus a. Since I have the negative sign here, I'm going to substitute 0 first. That will flip it. So it's going to be e to 0 minus e to negative s plus a multiplied by infinity. Now I could have closed the door, but why did I go and let them know?
Teach them a lesson.
Because people are not aware. Usually when you walk, you don't think there are people are in classes. So like you're not paying attention. So it's good to get their attention. Okay. And at the same time, to also let you know when you're in the hallway, assume there's a class. Okay. Everybody, is this clear? Everybody, what we've done? We switched the limits of the integration. What is this going to equal to? 1 over s plus a multiplied. What is e to 0? 1. What is e to negative s plus a multiplied by infinity? How is it 0? It's going to be e to the infinity multiplied by s plus a. What is this going to equal to? Well, it's going to be 0. No, don't laugh yet. But when is it going to be 0? Is it going to be 0? Under certain conditions, which is the real part of this exponential has to be greater than 0. So the real part of s plus a is greater than 0. Why? If the real, this s is complex, so it has the real part and imaginary part. I'm going to take the real parts of both of these together. If the real part is multiplied by infinity and multiplied by as a negative, what is that going to equal to? A 0. What is negative? What is e to negative 5 multiplied by infinity? 0. Agree? What is e to 5 multiplied by infinity? Infinity. So when is this going to be equal to a 0? Only if the real part multiplied by the infinity is greater than 0. Is that clear? Because I have a negative sign already here. There's a negative sign, there's a negative sign. This part, the real part of it, has to be greater than 0. So it has to be like this positive 5 for all this to be equal to a 0. Make sense? Anybody understood that? E to negative 5 multiplied by infinity is 0. What is e to negative 5 multiplied by infinity? Minus j 6 multiplied by infinity. What is this going to equal to? If you answer correctly, we'll end the class.
0.
This is going to equal to a 0. Okay, good. What is e to negative 5 multiplied by infinity plus j 6 multiplied by infinity?
0.
Who said 0?
It's a
Excellent. What is the exponential? This exponential part does not affect the magnitude. Is that clear? E to j x, what is e to j x equal to? What is the magnitude of e to j any number? What is the magnitude of this? 1. 1. The magnitude is always 1. So this part, I can write this as e to negative 5 multiplied by infinity multiplied by e to j 6 multiplied by infinity. Agree? This, the magnitude of it, is always equal to a 1. This is innocent, even though it has all this infinity. But this is a sinusoidal signal. The magnitude of it is always a 1. If I multiply it by a 0, it's going to become a 0. Does that make sense, everybody? And that's why I want the real part. The imaginary part does not matter. The imaginary part multiplied by infinity is going to have a magnitude of 1. The real part is going to determine the magnitude. Clear? Okay, we'll finish in a second. Since we're not going to see you for a week. Okay. So what does that mean? we want the real part of S plus A to be greater than 0, and therefore the real part of sigma plus j omega, which is the value of S, plus A greater than 0. What is the real part of all this? It's going to be sigma plus A greater than 0, which means sigma has to be greater than negative A. What does this give me? Anybody? That gives me the region of convergence. This is negative A. This is the region of convergence. Sigma has to be greater than negative A for this integration to converge. Together? Okay, we'll stop here, but I'm going to take attendance.